Awesome. Now we're into part 6, and we're going to start with number 32. So we're asked to make a sketch of a degree 4 polynomial with the following properties. We have a positive 0 and 2 negative zeros. One of those has order 2. We have a positive y-intercept. And we're given the end behavior, that as x goes to negative infinity, the function goes to negative infinity. And as x carries on to infinity, y will decrease down to negative infinity. So if we kind of go to our graph, we know that we're going to be coming up from negative infinity, and we're going to be going down to negative infinity. So that kind of takes care of that. We know we have a positive y-intercept, so I'm just going to kind of pick a value, go ahead and draw it. As far as the right side of the graph goes, we know we have one positive 0. So I can just go ahead and just kind of sketch that. That would be our positive 0, so we're good on that. Then we have 2 negative zeros, one with multiplicity 2. So when we have multiplicity 2, that means that we know that there's going to be kind of like a bounce. So it'll hit the y, or it'll hit the x-axis and then bounce and then keep going. So what I'm going to do is I'm going to, go ahead and draw it kind of hitting. It's going to bounce, and then it's going to continue down. So hit the axis, bounce, and then keep going down. There we go. Perfect. So that takes care of, we have 2 negative zeros here. Here, this one has order 2. We have a positive y-intercept, and our end behavior is completely right. So we're all good. Moving on to 33, we're given information about where zeros are, -5, 0, and 3. So we know we'll have a 0 here. Kind of estimate our other 2. Passes through the point -1a. So at around -1, we'll have some value a. I'll just go ahead and sketch this point where a is a positive real number. And we know that our end behavior is that as x goes to negative infinity, p of x goes to negative infinity. And as x goes to positive infinity, p of x will also decrease. So again, kind of like the last time, we know we're going to kind of go like this. We're asked which zeros could possibly have an order of 2, and we're asked to explain. So starting from the left, I know that I'm coming up, and I know I have to go through this point. So if I have multiplicity 2 here, I would come up and come back down. I can't ever hit that point up there. So I know that at -5, that will have an order of 1 because it has to go through this point. Then from there, I can either draw my graph like this or like that. Let me draw that with a different color. I could either draw my graph the first way or I could draw it the second way. Either way, it has the correct end behavior, passes through the point that we need to pass through, and it has the right zeros. So that means that either 0 or 3 could be our double roots. And that's just because we know that it cannot be 5, but the other 2 are non-restricted. That again is just because if we hit 5, we have to go through this point, but if we go up through 5 and bounce, we will never be able to hit that point if it had multiplicity of 2. So there we go. On to number 34. We're given this rational function. We're asked to find our horizontal and vertical asymptotes, determine if there's any holes in the graphs, give their coordinates, then we're asked for the domain in interval notation. So as far as determining our asymptotes goes, that is going to require us to kind of factor out our rational function if it is possible to do so. So on top we have a binomial. We know that those can't be factored, but this quadratic down here, that should be able to be factored. So if I go ahead and do that, I'll have x plus 8 over two numbers that multiply to negative 16 are 8 and negative 2. And then this is 6 is the same as 8 minus 2. So we know that we'll have over x plus 8, x minus 2. So then notice we have something on top that's the same as on bottom. So those can cancel out, and we would be left with 1 over x minus 2. Now, just to make sure we're on the same page, these two functions aren't necessarily the same. This is just what happens if you simplify that one. So this is simplified. So if we think about our horizontal asymptotes, as we graph this function, that's going to kind of look like this, right? So because we have an x on the bottom in the simplified version and none on top, we know that our horizontal asymptote is going to be y equals 0. Now, as far as our vertical asymptote, that'll come from the x values that make it so that we divide by 0. So when x minus 2 is equal to 0, that means that x equals 2, and that will be our vertical asymptote. So if I were to kind of draw those on my graph over here, let me resketch this a little bit, just kind of clean it up. My function will kind of look like this. My vertical asymptote here will be x equals 2. My horizontal asymptote will be y equals 0. So this, let me just retouch that a little bit, should not be crossing through. Keep approaching, but never quite get there. There we go. Now we're asked to determine if there's any holes in the graph. Holes will come from whenever we have a binomial that cancels out from the top and bottom. So if we remember back, we canceled out that x plus 8. So that when we simplified it, we didn't have that show up anymore. So the hole will come up when x plus 8 is equal to 0, or when x is equal to negative 8. And again, x plus 8 is just because that's the binomial that was canceled out above. Excuse me. So we know that when x equals negative 8, there should be a hole. In order to find that point, we'll plug it into the simplified version. So this up here. So if I plug that into our function or our factored version, we would end up with a 0 over 0, and that's not, that doesn't work, right? So I will plug it into 1 over negative 8 minus 2, which should be negative 1/10, which means that there's a hole at negative 8, negative 1/10. Perfect. Now, as far as our domain, that gives us the valid x values that we can plug in, right? So if I know that there's a hole, that means I know that x cannot be negative 8. My vertical asymptote will also interrupt my x values. So again, my vertical asymptote was x equals 2. Oh, so that means that this, just to make sure we're all good, the sketch of our graph should look like this. So we'll have our vertical asymptote x equals 2, the horizontal one, sorry about that, should be y equals 0. And then we'll have a hole over here, x equals -8. So, going back to our domain, we know that x cannot be -8 and x cannot be -2. So those are the two values where, x cannot be +2. So those are the two places where it does not work, which means that our domain should be from -infinity up to -8. Then we'll have a union. We'll go from -8 to 2, another union, and then from 2 up to infinity. And that will be our domain. There we go. On to our last page, at number 35, we're asked to find an example of a rational function with a vertical asymptote at x equals -5, 0 at x equals 3, a hole at x equals -6. We have these properties of our endpoint. So I'm going to go through each of those and just kind of dissect what each of those mean for our function. So we know it's rational, so I should have a fraction of some polynomial on top over a polynomial on the bottom, right? So if I know that I have a vertical asymptote at x equals -5, that means we'll have x plus 5 in the denominator. So that means x plus 5 will go down here. Now we know we have a 0 at x equals 3. That means x minus 3 is going to be in the numerator. And that just comes from, if we think about it, we want to be able to plug in 3 and end up with a 0 on top. So I want to have a 0, so I want to have a 0 over something else, and this satisfies that. We know we have a hole at x equals -6, so that means x plus 6 in both the denominator and the numerator. So let me go ahead and take this, and that. So we know we have x minus 3 in the numerator. Then I know I have x plus 6 in both. Now we're given our n properties up here. So as far as the function, let me go ahead and clean this up a little bit. We know that this will have a power, we know that we'll have an x squared on top, and x squared on bottom, plus all the other stuff, right? Because we're given two binomials. So that means that the limit will be equal to the coefficient on top, the coefficient of x squared on top, so let's say that's a, over b. So as we go to infinity, we'll have, it'll end up just being that, because as we get bigger and bigger and bigger, the only terms that will matter will be the highest powers of x. So those will end up, limit will kind of look like this, which will be a over b. So what I'm going to do is I'm going to introduce a -2 into our numerator. And that way we'll end up with -2x squared plus everything else over x squared plus everything else. So we take the limit, we'll have -2 over 1, which is just -2. And that gives us a rational function of this. There we go. Moving on to number 36, we're asked to evaluate these limits. So for a, on top, we know that our highest power is 3x squared, and in the denominator, we're given 2x squared. So that means as the limit proceeds, this is the same as the limit as x goes to infinity 3x squared over 2x squared. So the x squareds would cancel out, and you know that should be 3 over 2. There we go. For part B, I can think about 8x to the negative 3 as 8 over x cubed plus 5x to the negative 1 is the same as 5 over x. We have a plus 1 at the end. So I know that if x is going to negative infinity, that means that this number down here is going to get very negative but also very large. So if I take 8 and I divide it by a really, really big number, an infinitely big number, this is going to decrease to 0. 5 will have the same thing happen to it. Then I know that my limit will end up just being 1. On to number 37. We're asked to find a possible formula for the rational function that is described here. So we have two vertical asymptotes, x equals negative 2, x equals negative 3. So that to me says that I know that I'm going to have x plus 2 and x minus 3 in our denominator. So I know that when I go to write my function, it'll be something over x plus 2, x minus 3. We know we have a horizontal asymptote of x equals 0, so that means power on bottom is greater than power on top. We know that it crosses the x-axis once at x equals 5. Now crossing the x-axis, that's the same as having a 0, right? So we could say 0 at x equals 5, or we know that x minus 5 is in the numerator. So let me go ahead and add that. And then we know it passes through this point 4, 0.5. Now, from the get-go, I don't know that that is necessarily true for this function. So what I'm going to do is I'm going to add an a in front that we can use to kind of scale our equation, right? So we know that g of x will look like this. I know that g of 4 would be the same as plugging in 4 plus 2, 4 minus 3, and that should be equal to 0.5. So now, continuing on, I know 4 minus 5 is negative 1, so we have negative a over 4 plus 2 is 6, 4 minus 3 is 1. Again, that's still equal to 0.5. So I know that negative a over 6 is 0.5, or a is equal to negative 3. So that means our function, g of x, is negative 3 x minus 5 over x plus 2 times x minus 3. There we go. Perfect. Thank you so much for watching, and good luck on your exam. Thank you.